Hello there, and welcome to the Sleepy Science Channel. I'm so glad you found your way here tonight. Maybe you've had a long day filled with the usual rush and noise of everyday life, or perhaps you're someone who finds peace in contemplating the deepest mysteries of our universe rather than counting sheep. Either way, tonight's journey is specially crafted for you. You've got nothing to do but rest now. Let your mind relax, your breathing slow, and your body grow light as if the very fabric of space and time has gently loosened around you. Because tonight, we're not simply stargazing from Earth's familiar surface. We're drifting into the deepest mysteries of space itself, exploring the most enigmatic objects in the entire cosmos, black holes. These are not the destructive monsters of science fiction, but rather nature's most elegant expressions of gravity and time. They are cosmic sculptures carved from collapsed stars, gateways where the familiar laws of physics dance at their very limits. We'll journey gently from their violent births to their patient deaths, from the event horizons that mark their boundaries to the singularities that hide their deepest secrets. You'll hear of supermassive giants slumbering at the hearts of galaxies, of stellar wanderers drifting invisibly through space, and of the first photograph ever taken of a black hole's shadow. Some of what you discover tonight may surprise you, filling you with quiet wonder as you drift toward sleep. And just before we begin our cosmic journey, if these gentle explorations help you unwind and find peace at the end of your day, consider liking and subscribing to the channel. It helps other restless souls find their way here too, one peaceful night at a time. Now, let's begin our descent into the beautiful darkness of deep space. Chapter 1: The Birth of Darkness. Black holes are born from the deaths of the most massive stars in the universe. Not every star can become a black hole. Most stars, like our Sun, will end their lives more gently, swelling into red giants, before quietly fading to white dwarfs. But the universe's most massive stars, those born with at least 20 or 30 times the mass of our Sun, face a very different destiny. They burn bright and fast, consuming their nuclear fuel in just millions of years rather than billions. The core of a massive star undergoes catastrophic collapse in less than 1 second. When a massive star exhausts its nuclear fuel, the outward pressure from fusion reactions can no longer balance the inward pull of its own gravity. What happens next is almost impossible to comprehend in its speed and violence. The star's core, an object perhaps the size of Earth but containing more mass than our Sun, collapses completely in a fraction of a second. It's a cosmic implosion of unimaginable intensity, yet it happens in perfect silence, witnessed only by the distant light of stars. The collapsing core becomes so dense that not even neutron degeneracy pressure can stop it. In less massive stellar deaths, the collapse halts when the core becomes a neutron star, where matter is compressed to the density of atomic nuclei. But beyond a certain mass limit, called the Tolman-Oppenheimer-Fokoff limit, even this ultimate form of matter cannot resist gravity's pull. The neutrons themselves are crushed beyond recognition, and matter falls inward with nothing left to stop it. A supernova explosion announces the birth of most black holes. As the core collapses, the outer layers of the star rebound in a tremendous explosion that can briefly outshine an entire galaxy. This supernova blast scatters heavy elements across space: the calcium in your bones, the iron in your blood, all forged in such stellar furnaces and distributed by these cosmic catastrophes. Yet, at the heart of this brilliant explosion, darkness is born as the collapsed core disappears behind an event horizon. The escape velocity at a black hole's surface exceeds the speed of light. Every object has an escape velocity, the minimum speed needed to break free from its gravitational pull. Earth's escape velocity is about 11 kilometers per second. The Sun's is 617 kilometers per second. But at the surface of a black hole, the escape velocity exceeds 300,000 kilometers per second, the speed of light itself. Since nothing can travel faster than light, nothing can escape. Black holes are not actually holes, but objects of extreme density. The name black hole suggests empty space, a void or tunnel through the fabric of reality. But black holes are quite the opposite. They are objects so massive and compact that they warp space and time around them into impossible geometries. They are made of matter, the same matter that once formed the core of a massive star, now compressed to a point of infinite density that we call a singularity. The boundary around a black hole is called an event horizon. This invisible boundary marks the distance from a black hole where the escape velocity equals the speed of light. It's not a physical surface you could touch, but rather a point of no return in space itself. Cross this boundary and you can never send a signal back to the outside universe. The event horizon is like a one-way membrane through which information can enter but never leave. Time itself slows down near a black hole due to gravitational time dilation. Einstein's theory of relativity tells us that gravity affects the passage of time. The stronger the gravitational field, the slower time moves relative to distant observers. Near a black hole, this effect becomes extreme. What seems like hours to someone falling toward a black hole might appear to last eternally to someone watching from a safe distance. Time stretches like taffy in the grip of intense gravity. The size of a black hole depends only on its mass. A black hole's event horizon has a radius directly proportional to its mass. This radius, called the Schwarzschild radius, would be about 3 kilometers for a black hole with the mass of our Sun. The more massive the black hole, the larger its event horizon. A black hole with the mass of Earth would have an event horizon smaller than a marble, while the supermassive black hole at the center of our galaxy has an event horizon larger than Mercury's orbit. Stellar mass black holes typically contain between 3 and 20 times the mass of the Sun. These are the black holes born from individual massive stars, and they represent the most common type in our galaxy. They are scattered throughout the Milky Way like invisible landmarks, most of them completely dark and detectable only through their gravitational effects on nearby stars or gas clouds. Astronomers estimate there may be hundreds of millions of these stellar mass black holes drifting silently through our galaxy. Some black holes may have formed in the early universe without stars. Not all black holes require the death of a massive star. In the chaotic early universe, regions of space with unusually high density might have collapsed directly into primordial black holes. These theoretical objects could have masses ranging from microscopic to stellar scales, formed not from stellar evolution but from the initial conditions of the cosmos itself. They remain one of the great mysteries in our understanding of the early universe. Black holes can be born in binary systems, creating exotic cosmic dancers. When massive stars form in pairs, both may eventually become black holes, creating a binary black hole system. These pairs spiral around each other, gradually losing energy by emitting gravitational waves, ripples in the fabric of spacetime itself. Eventually, after millions or billions of years, they merge in a violent collision that releases more energy in gravitational waves than all the stars in the observable universe emit in light. The formation of a black hole marks the end of a star's nuclear burning forever. Once matter crosses the event horizon, it can no longer participate in the nuclear processes that power stars. The black hole represents the ultimate endpoint of stellar evolution, a place where the familiar processes of nuclear fusion have given way to something far more exotic. It's a cosmic full stop, marking the end of one story and the beginning of another, stranger tale. Even now, as you rest in the gentle darkness of night, somewhere in our galaxy a massive star is approaching the end of its life. Its nuclear fires are beginning to flicker and fade. Soon, perhaps tonight, perhaps tomorrow, it will undergo that final catastrophic collapse, and another black hole will be born in perfect silence, adding its invisible presence to the cosmic dark. In this way, the universe continues its ancient cycle of creation and destruction, matter and energy dancing their eternal dance through the vast theater of space and time. Chapter 2: The Edge of Everything. The event horizon is the boundary beyond which nothing can escape a black hole. This invisible sphere marks the ultimate point of no return, where the gravitational pull becomes so strong that even light, the fastest thing in the universe, cannot break free. It's not a physical barrier you could touch or see, but rather a boundary in space itself, as fundamental as the distinction between up and down, or between past and future. The event horizon exists as a quiet threshold between our familiar universe and something utterly alien. From the outside, time appears to stop at the event horizon. If you could watch someone fall into a black hole from a safe distance, you would see something extraordinary and unsettling. As they approached the event horizon, they would appear to slow down dramatically, their movements becoming more and more sluggish. Their light would redshift, growing dimmer and redder until they seemed to freeze just at the edge, suspended there forever like a photograph. But this is just an illusion of perspective. The falling person experiences no such slowdown. For someone crossing the event horizon, the experience is surprisingly unremarkable. Despite what outside observers might see, a person falling past the event horizon would experience nothing special at the moment of crossing. They would not hit a wall or feel a sudden change. The laws of physics would continue to operate normally around them, at least initially. They would simply continue falling inward, unaware that they had passed the point of no return, unaware that they could never signal back to the universe they had left behind. The size of an event horizon is proportional to the black hole's mass. The more massive a black hole, the larger its event horizon. This relationship is beautifully simple and precise. Double the mass and you double the radius of the event horizon. A black hole with the mass of our Sun would have an event horizon about 6 kilometers across. The supermassive black hole at the center of our galaxy, containing over 4 million solar masses, has an event horizon larger than the orbit of Mercury. Nothing, not even information, can escape from inside the event horizon. This absolute boundary has profound implications for physics and philosophy. Once information crosses the event horizon, it can never return to the outside universe. This creates puzzles that physicists are still working to understand. How can information truly disappear from the universe? The question touches on the deepest foundations of physics, connecting gravity, quantum mechanics, and thermodynamics in ways we don't yet fully comprehend. The surface area of an event horizon can never decrease. This remarkable property, discovered by physicist Stephen Hawking, means that when black holes merge, the total area of their event horizons always increases. Even when a black hole evaporates due to Hawking radiation, the process is so slow that, for all practical purposes, event horizons only grow. It's as if the universe keeps a careful accounting of information, recording every particle that falls past the point of no return. Event horizons are perfectly spherical in the simplest case. For a black hole that is not rotating and has no electric charge, the event horizon forms a perfect sphere around the central singularity. This Spherical symmetry reflects the fundamental nature of gravity itself, pulling equally in all directions. It's a form of mathematical perfection, a sphere drawn not in space but in the very geometry of spacetime itself. Rotating black holes have oblate event horizons that bulge at the equator. When a black hole spins, it drags spacetime around with it in an effect called frame dragging. This rotation distorts the shape of the event horizon, making it slightly flattened like a spinning ball of dough. The faster the spin, the more pronounced this effect becomes. At the maximum possible rotation rate, the event horizon develops sharp corners at its poles, creating one of the most exotic shapes in physics. The event horizon of a rotating black hole has two layers. Fast-spinning black holes have an additional boundary called the ergosphere, which lies outside the static limit where objects must rotate. With the black hole between the ergosphere and the event horizon, space itself is dragged around so violently that nothing can remain stationary. Even light must participate in the black hole's rotation, creating regions where cause and effect become twisted in ways that challenge our understanding. Tidal forces near the event horizon can stretch objects into long, thin shapes. As you approach a black hole, the gravitational pull on your feet becomes significantly stronger than the pull on your head, creating a stretching force called a tidal effect. For stellar mass black holes, these tidal forces become extreme well before you reach the event horizon, stretching any object into a long, thin strand. This process, sometimes colorfully called spaghettification, would be fatal long before you crossed into the black hole proper. Supermassive black holes have gentler tidal forces at their event horizons. Paradoxically, the largest black holes are the gentlest at their boundaries. The event horizon of a supermassive black hole is so large that the tidal forces there are relatively mild. You could, in principle, cross the event horizon of such a black hole and survive for some time before the increasing tidal forces deeper inside became fatal. The universe's most massive objects are, in some ways, the most forgiving. Light rays can orbit a black hole just outside the event horizon. At a distance of 1.5 times the Schwarzschild radius, light rays can follow circular orbits around a black hole, neither falling in nor escaping to infinity. This region, called the photon sphere, creates a kind of cosmic lighthouse where light can circle the black hole multiple times before either escaping or spiraling inward. It's a place where light itself becomes trapped in an eternal dance around the darkness. The event horizon represents the ultimate limit of causality. Inside the event horizon, cause and effect become divorced from the outside universe. Events occurring within can never influence anything beyond that boundary. It's as if the event horizon creates a separate bubble of causality, a region of spacetime that has become disconnected from the rest of reality. What happens inside stays inside, forever and always. Virtual particles near the event horizon can become real through Hawking radiation. Quantum mechanics tells us that empty space is not truly empty but filled with pairs of virtual particles that constantly appear and annihilate. Near an event horizon, one particle from such a pair can fall into the black hole while the other escapes, becoming real in the process. This mechanism slowly evaporates the black hole, causing it to lose mass and energy over timescales so vast they dwarf the current age of the universe. As you drift toward sleep tonight, imagine floating safely in the emptiness of space, far from any black hole, watching these mysterious boundaries shimmer in the darkness like soap bubbles made of warped space-time. The event horizons are out there, scattered throughout our galaxy, marking the edges of regions where our familiar physics gives way to something far stranger. They are the universe's ultimate boundaries, gentle and invisible, patient and eternal, keeping their secrets locked away in the cosmic dark. In their silent presence, space and time themselves are transformed, creating pockets of mystery that may forever remain beyond our full understanding. Chapter 3: Hearts of Darkness. At the center of every black hole lies a singularity where density becomes infinite. This is perhaps the most mysterious concept in all of physics, a point where matter is compressed to infinite density and space-time curvature becomes infinite. Our mathematics breaks down at the singularity, unable to describe what happens there. It represents the limit of our understanding, a place where the familiar laws of physics simply stop working and point toward something beyond our current knowledge. A singularity has zero volume but contains all the mass of the collapsed star. All the matter that falls into a black hole, including the original stellar core that created it, becomes compressed into a mathematical point with no spatial extent. This seems impossible to imagine, yet it follows inevitably from Einstein's equations of general relativity. The singularity is not an object in space, but rather a boundary of space itself, a place where our usual concepts of size and distance lose all meaning. Time and space become interchanged near a singularity. In the extreme gravitational field near a singularity, the normal relationship between space and time breaks down completely. The direction toward the singularity becomes time-like rather than space-like, meaning that approaching the singularity becomes as inevitable as the forward flow of time itself. Once inside an event horizon, all paths through space and time lead inexorably toward this central point. The singularity may not actually exist as a physical point. Many physicists believe that the mathematical singularity of general relativity is a sign that our theory is incomplete rather than a description of physical reality. When a theory predicts infinite values, it usually means we need a better theory. Quantum effects, which become important at incredibly small scales, may prevent the formation of true singularities, replacing them with something exotic but finite. Quantum mechanics may transform singularities into something else entirely. At the incredibly tiny scales near what we call a singularity, quantum effects should become dominant over classical gravity. Some theories suggest that quantum mechanics might prevent infinite compression, creating instead a quantum bounce or a transition to another region of space and time. The truth is that we simply don't know what happens in these extreme conditions where quantum mechanics and gravity meet. Different types of black holes may have different types of singularities. A non-rotating black hole should have a point singularity at its center, while a rotating black hole may have a ring singularity along its equatorial plane. These ring singularities are even more mysterious than point singularities, potentially creating closed time-like curves and other exotic effects that challenge our understanding of causality and the structure of time itself. The singularity is hidden behind the event horizon and can never be directly observed. This is one of the most important principles in black hole physics, the cosmic censorship hypothesis. It suggests that singularities are always hidden from outside observers by event horizons. We can never directly observe a singularity or receive information from one, protecting the rest of the universe from the breakdown of physics that occurs there. The event horizon acts like a curtain, preserving the universe's modesty. Falling into a singularity would involve experiencing infinite tidal forces. As you approached a classical singularity, the tidal forces stretching your body would grow without limit. Your feet would be pulled infinitely harder than your head, stretching you into an infinitely thin strand. But this process would happen so quickly that you might not even experience it, reaching the singularity in a finite amount of your own proper time. The laws of thermodynamics become strange near singularities. Normally, the entropy of a black hole is proportional to the area of its event horizon, not its volume. This means that black holes have the highest entropy possible for objects of their size. Near the singularity, where spacetime itself becomes ill-defined, even these thermodynamic relationships break down, leaving us with more questions than answers about the nature of information and energy. Some theories suggest singularities could be gateways to other parts of the universe. In certain mathematical solutions to Einstein's equations, singularities connect to other regions of spacetime, creating what physicists call Einstein-Rosen bridges or wormholes. These hypothetical tunnels through space and time could, in principle, connect distant parts of our universe or even link to entirely different universes. However, such connections would likely be highly unstable and collapse before anything could pass through them. The information paradox centers on what happens to information at singularities. When matter falls into a black hole, it carries information about its quantum state. If this information is destroyed at the singularity, it would violate one of the fundamental principles of quantum mechanics, which states that information can never be truly lost. This paradox has puzzled physicists for decades and has led to various proposed solutions, from information being encoded on the event horizon to the possibility that black holes eventually evaporate and release their information back to the universe. Naked singularities, if they exist, would be singularities without event horizons. Some solutions to Einstein's equations allow for singularities that are not hidden behind event horizons. These naked singularities would be visible to outside observers, potentially allowing us to see the breakdown of physics directly. However, the cosmic censorship hypothesis suggests that such objects cannot form through realistic physical processes, though mathematically they remain intriguing possibilities. The singularity represents the ultimate frontier of human knowledge. In a sense, singularities mark the boundary between the known and unknowable. They represent regions where our best theories fail, where our most fundamental concepts lose meaning. Yet they may also point the way toward new physics, new understandings of space, time, matter, and information. They are cosmic laboratories where nature experiments with the very foundations of reality. Even the question of whether singularities exist is still debated among physicists. Some argue that the appearance of infinities in our equations simply means we need better theories. Others suggest that singularities may be real features of the universe, places where the normal rules simply don't apply. Still, others propose that quantum effects, string theory, or other new physics might resolve the paradoxes, replacing the mathematical singularity with something more physically reasonable but equally exotic. As you settle deeper into rest, let your mind wander to these ultimate mysteries hidden at the hearts of black holes. Somewhere in the darkness of space, these enigmatic points exist, challenging everything we think we know about reality. They are cosmic question marks, written in the language of gravity and spacetime, waiting for future generations of scientists to decipher their meaning. Whether they represent the ultimate limits of knowledge or gateways to new understanding, they remain among the universe's most profound and beautiful mysteries, hidden safely behind their event horizons, keeping their secrets in the gentle darkness of the cosmic night. Chapter 4: Giants at the Center. Supermassive black holes contain millions to billions of times the mass of our Sun. These cosmic giants dwarf their stellar mass cousins, containing as much mass as entire star clusters compressed into regions smaller than our solar system. The supermassive black hole at the center of our own Milky Way, known as Sagittarius A*, contains over 4 million times the mass of the Sun. Some of the largest known supermassive black holes contain more than 60 billion solar masses, making them among the most massive individual objects in the universe. Nearly every large galaxy has a supermassive black hole at its center. This remarkable fact suggests a deep connection between the formation and evolution of galaxies and their central black holes. The mass of a galaxy's central black hole is closely related to the mass of its central bulge of stars, hinting at a cosmic dance between black hole growth and star formation that has shaped the structure of the universe for billions of years. Supermassive black holes formed very early in the universe's history. Astronomers have discovered supermassive black holes in galaxies so distant that we see them as they were when the universe was less than 1 billion years old. This presents a puzzle. How did these giants grow so massive so quickly? The early universe was a very different place, denser and more chaotic, and these conditions may have allowed black holes to grow much faster than they do today. The formation of supermassive black holes remains one of astronomy's greatest mysteries. Several theories attempt to explain their origin. They may have grown from the first generation of massive stars, called population 3 stars, which were much larger than stars today. Alternatively, they might have formed directly from the gravitational collapse of massive gas clouds in the early universe, bypassing the stellar phase entirely. The truth may involve a combination of these processes. Sagittarius A sits quietly at the center of our galaxy. Our own galactic center harbors a supermassive black hole that, for now, feeds very gently on surrounding material. Occasionally, astronomers observe flares of radiation as gas clouds or stars venture too close, but most of the time, Sagittarius A** remains surprisingly quiet. It's a sleeping giant, containing the mass of millions of suns while producing less light than a single star. Supermassive black holes can dramatically affect star formation in their host galaxies. When these giants feed actively, they can produce jets of material and intense radiation that heat the surrounding gas, preventing it from cooling and forming new stars. This creates a feedback mechanism that regulates both the growth of the black hole and the formation of stars throughout the entire galaxy. In this way, supermassive black holes help shape the evolution of galaxies over cosmic time. Active galactic nuclei are powered by feeding supermassive black holes. When matter falls into a supermassive black hole, it forms an accretion disk that can become incredibly hot and luminous. These active galactic nuclei can outshine all the stars in their host galaxies combined, making them visible across billions of light years. They are some of the most luminous objects in the universe, powered entirely by gravity. Quasars are among the most distant and luminous objects we can observe. These quasi-stellar objects are actually the active nuclei of very distant galaxies, powered by supermassive black holes, consuming vast amounts of matter. Because they are so distant, we see them as they were billions of years ago, when the universe was young and these black holes were growing rapidly. They provide windows into the early stages of cosmic evolution. Some supermassive black holes produce jets that extend for millions of light years. When material falls into a rapidly spinning supermassive black hole, some of it can be accelerated and ejected in narrow jets traveling at nearly the speed of light. These jets can extend far beyond their host galaxies, creating enormous radio-bright structures that dwarf entire galactic clusters. The mechanism that creates these jets is still not fully understood. Binary supermassive black holes may exist in some galaxy centers. When galaxies merge, their central supermassive black holes should eventually form binary systems, spiraling around each other, while emitting gravitational waves. These systems are extremely difficult to detect directly, but astronomers have found indirect evidence for them in the form of periodic variations in the light from some quasars and galaxies. The event horizons of supermassive black holes are enormous. The supermassive black hole in the galaxy M87, with a mass of about 6.5 billion suns, has an event horizon larger than the orbit of Neptune. You could fit our entire solar system inside its event horizon with room to spare. Despite containing billions of times the mass of the Sun, these objects have surprisingly low average densities because their event horizons are so large. Supermassive black holes grow by accretion and mergers. These giants increase their mass in two main ways: by consuming surrounding gas, dust, and stars, and by merging with other black holes when their host galaxies collide. The merger of two supermassive black holes is one of the most energetic events in the universe, producing gravitational waves that can be detected across cosmic distances. The sphere of influence of a supermassive black hole can extend for hundreds of light-years. This is the region where the black hole's gravity dominates the motion of stars and gas. Within this sphere, stars orbit the black hole rather than participating in the general rotation of the galaxy. Studying the orbits of stars within this region is one of the primary ways astronomers measure the masses of supermassive black holes. Some supermassive black holes may have intermediate mass partners. Recent observations suggest that some galaxies may harbor multiple black holes of different masses. These intermediate mass black holes, containing hundreds to thousands of solar masses, may be the missing link between stellar mass and supermassive black holes. They might represent an intermediate stage in black hole evolution or form through different processes entirely. Even now, as our galaxy slowly rotates through space, Sagittarius A* sits at its center like a massive anchor point around which hundreds of billions of stars orbit. It's a cosmic lighthouse that rarely shines, a giant that sleeps peacefully in the heart of our stellar island home. Across the universe, countless other supermassive black holes rest in the centers of their galaxies, some feeding actively and lighting up the cosmos, others waiting patiently in the dark. They are the universe's largest gravitational sculptors, shaping the formation and evolution of galaxies across cosmic time, silent monarchs ruling over vast stellar kingdoms from their dark thrones. Chapter 5. The Dance of Gravity. Black holes warp the fabric of spacetime like bowling balls on a stretched sheet. Einstein's theory of general relativity revealed that massive objects don't pull on other objects through some mysterious force, but instead curve the geometry of space and time itself. A black hole creates such an extreme curvature that spacetime becomes like a deep well with infinitely steep sides. Objects don't fall into black holes because they're pulled, but because they're following the curved paths that spacetime provides. Time passes more slowly in stronger gravitational fields. This effect, called gravitational time dilation, means that clocks run slower near massive objects. Near a black hole, this effect becomes extreme. If you could hover just outside the event horizon of a black hole for what felt like an hour to you, observers far away would see millions of years pass. This isn't science fiction, but a real consequence of gravity's effect on the flow of time itself. Light bends when it passes near a black hole, creating gravitational lensing. Even though light has no mass, it follows the curves in spacetime created by massive objects. When light from distant stars passes near a black hole, it bends around the black hole's intense gravitational field. This can create multiple images of the same star, or stretch the star's image into arcs and rings. The black hole acts like a cosmic magnifying glass, bending light in ways that reveal its presence even when it emits no light of its own. Black holes can have stable circular orbits at specific distances. Just as planets orbit the Sun, objects can orbit black holes at various distances. The innermost stable circular orbit depends on the black hole's spin. For a non-rotating black hole, this innermost stable orbit is located at 3 times the Schwarzschild radius. Closer than this, no stable circular orbits are possible, and anything there will spiral inexorably inward. The ergosphere of a rotating black hole drags spacetime around with it. When a black hole spins, it doesn't rotate alone but drags the very fabric of spacetime along with it in an effect called frame dragging. This creates a region called the ergosphere, outside the event horizon, where spacetime itself is forced to rotate. Nothing within the ergosphere can remain stationary with respect to distant observers, no matter how powerful their rockets. Tidal forces from black holes can tear objects apart before they reach the event horizon. The gravitational force from a black hole is stronger at closer distances. This means that if you were falling feet first toward a black hole, your feet would experience a stronger pull than your head. For stellar mass black holes, this difference becomes extreme well before you reach the event horizon, stretching you into a long, thin shape. This process occurs because gravity falls off as the inverse square of distance, creating differential forces across any extended object. Some orbits around black holes are chaotic and unpredictable, while there are stable circular orbits. At certain distances, many possible orbits around black holes are chaotic, meaning that tiny changes in initial conditions can lead to dramatically different outcomes. An object might orbit stably for thousands of years before a small perturbation sends it spiraling inward or escaping to infinity. This chaos arises from the complex interplay between the black hole's gravity, the object's motion, and relativistic effects. Binary black hole systems create ripples in spacetime called gravitational waves. When two black holes orbit each other, they lose energy by emitting gravitational waves, which are literally ripples in the fabric of spacetime itself. As they lose energy, the black holes spiral closer together, orbiting faster and faster until they finally merge in a catastrophic collision. These waves travel outward at the speed of light, carrying information about the collision across the universe. The final moments of a black hole merger are incredibly violent and brief. In the last fraction of a second before two black holes merge, they can orbit each other hundreds of times per second, releasing more energy in gravitational waves than all the stars in the observable universe emit in light. The collision itself happens so quickly that the entire merger, from the final spiral to the formation of a single black hole, takes less than a second. Gravitational waves from black hole mergers have been detected on Earth. The Laser Interferometer Gravitational Wave Observatory, LIGO, has successfully detected dozens of these cosmic collisions, measuring distortions in spacetime smaller than 1/10,000th the width of a proton. These detections have opened an entirely new window on the universe, allowing us to observe events that produce no light but shake the very foundations of space and time. Black holes can act as natural particle accelerators. The intense magnetic fields and curved spacetime near black holes can accelerate charged particles to incredible energies, sometimes approaching the speed of light. These accelerated particles can produce high-energy radiation, including X-rays and gamma rays, making black holes visible across vast distances despite their inability to emit light directly. The photon sphere is where light can orbit a black hole. At a distance of 1.5 times the Schwarzschild radius from a non-rotating black hole, photons can follow circular orbits. This creates a spherical region where light rays can circle the black hole multiple times before either falling in or escaping. From this distance, you could theoretically see the back of your own head as light from behind you orbits around the black hole and returns to your eyes. Retrograde orbits around black holes are closer to the event horizon than prograde orbits. Objects orbiting in the same direction as the black hole spin, prograde, have their innermost stable orbits farther from the event horizon than objects orbiting opposite to the spin, retrograde. This asymmetry arises from frame dragging effects and means that the black hole's rotation creates preferred directions. For orbital motion, black holes can focus gravitational waves like lenses focus light. When gravitational waves from distant sources pass near a black hole, the black hole's gravity can bend their paths, potentially focusing or defocusing the waves. This gravitational lensing of gravitational waves could allow us to detect signals that would otherwise be too weak to observe, effectively using black holes as cosmic amplifiers. As you rest tonight, imagine the invisible dance of gravity that surrounds every black hole in our universe. Space and time curve and flow like water around stones, creating cosmic whirlpools where the very geometry of reality becomes twisted and strange. Objects follow these curves not because they're pulled, but because curved spacetime provides no other path to travel. In this cosmic choreography, black holes serve as the universe's most dramatic dance partners, leading space and time through steps so complex that even our best physics struggles to follow their movements. The dance continues in perfect silence, visible only through its effects on light, matter, and the gentle ripples it sends through the fabric of existence itself. Chapter 6. Feeding the Darkness. Black holes consume matter through accretion disks of superheated gas and dust. When material falls toward a black hole, it doesn't plunge straight in but instead forms a swirling disk called an accretion disk. Conservation of angular momentum ensures that infalling matter spirals around the black hole many times before crossing the event horizon. As this material orbits closer and closer to the black hole, friction between particles heats the disk to temperatures of millions of degrees, causing it to glow brilliantly. Across the electromagnetic spectrum, accretion disks can become hotter than the cores of stars. The inner regions of an accretion disk around a stellar mass black hole can reach temperatures exceeding 10 million degrees Celsius hotter than the center of our Sun. This intense heat comes from the conversion of gravitational potential energy into thermal energy as matter spirals inward. The disk glows so brightly that it can outshine the combined light of billions of normal stars, making feeding black holes visible across vast cosmic distances. Matter in accretion disks moves at a significant fraction of the speed of light. In the innermost regions of the accretion disk, just outside the event horizon, matter can reach speeds of 10% to 30% the speed of light. At these relativistic speeds, the normal rules of physics begin to break down, and Einstein's special theory of relativity becomes crucial for understanding the disk's behavior. The material experiences time dilation and length contraction as it races around the black hole's event horizon. Black holes are remarkably efficient at converting mass into energy. Through the accretion process, black holes can convert up to 42% of infalling mass directly into energy, making them the most efficient energy conversion mechanisms in the universe. Nuclear fusion in stars, by comparison, converts only about 0.7% of mass into energy. This incredible efficiency explains why active galactic nuclei powered by supermassive black holes can be so luminous. Magnetic fields in accretion disks can launch powerful jets of material. The hot, ionized gas in accretion disks generate strong magnetic field lines that become twisted by the disk's rotation. These twisted magnetic fields can channel some of the infalling material away from the black hole, accelerating it to nearly the speed of light in narrow jets perpendicular to the disk. These jets can extend for millions of light years, carrying energy and material far from their source. Black hole jets can affect entire galaxies and galaxy clusters. The jets from supermassive black holes are so powerful that they can heat the gas in entire galaxy clusters, preventing it from cooling and forming new stars. This creates a feedback mechanism where the black hole regulates its own food supply by heating the surrounding material. In this way, supermassive black holes can influence star formation throughout their host galaxies and beyond. Tidal disruption events occur when stars wander too close to black holes. Occasionally, a star's orbit brings it within the tidal radius of a black hole, where the black hole's gravity becomes strong enough to overcome the star's own gravity. The star is then stretched and torn apart, with some material falling into the black hole while the rest is ejected at high speed. These events create distinctive flares of radiation that can be observed from millions of light years away. Black holes can consume entire stars over periods of months to years. When a star is tidally disrupted by a black hole, the disruption process happens quickly, but the subsequent accretion of stellar material can take much longer. The debris from the destroyed star forms an accretion disk that gradually feeds material into the black hole. Astronomers can observe these changing look events as normally quiet galactic centers suddenly brighten and then fade over months or years. Some black holes fast intermittently, creating variable brightness. Not all black holes feed at a steady rate. Some show dramatic variations in brightness over days, weeks, or years as their accretion rate changes. These variations can be caused by instabilities in the accretion disk, changes in the supply of material, or interactions with companion objects. The variability provides important clues about the physics of accretion and the environment around black holes. Quasars represent the most extreme examples of black hole feeding. These quasi-stellar objects are powered by supermassive black holes consuming material at nearly the maximum possible rate, called the Eddington limit. At this rate, the outward pressure of radiation from the hot accretion disk nearly balances the inward pull of gravity. Quasars can be trillions of times more luminous than our Sun, making them visible across billions of light-years. Black holes can strip material from companion stars in binary systems. When a black hole orbits close to a normal star, its gravity can pull material away from the star's surface. This stolen material forms an accretion disk around the black hole, creating an X-ray binary system. These systems flicker and vary in brightness as the accretion rate changes, and they're some of the brightest X-ray sources in our galaxy. The last stable orbit marks the point of no return for infalling material. At the innermost stable circular orbit, material in the accretion disk begins its final plunge toward the event horizon. Inside this radius, no stable orbits are possible, and matter falls inward in just a few milliseconds. This rapid final plunge causes the material to heat up dramatically, producing some of the most energetic radiation we observe from black holes. Accretion disks can be disrupted by the black hole's spin. Rapidly rotating black holes can cause their accretion disks to become warped or tilted through frame-dragging effects. In extreme cases, the inner and outer parts of the disk can become completely misaligned, creating complex three-dimensional structures that precess and wobble over time. These disruptions can affect the efficiency of accretion and the properties of any jets that form. Black holes may burp after consuming large amounts of matter. When a black hole suddenly consumes a large amount of material, such as during a stellar disruption event, it may subsequently eject some material in what astronomers playfully call a burp. These ejections can happen weeks or months after the initial feeding event and may be caused by instabilities that develop in the overloaded accretion disk. Even now, as you drift toward sleep, somewhere in our galaxy a black hole is feeding quietly in the darkness. Perhaps it's drawing thin wisps of interstellar gas into its accretion disk, heating them until they glow softly in X-rays. Or maybe it's patiently waiting for a wandering star to venture too close, ready to stretch and consume it over the coming months. These cosmic banquets happen in perfect silence, creating some of the most brilliant displays of light in the universe from objects that themselves emit no light at all. In the gentle darkness of space, black holes dine on starlight and shadow, transforming the matter of dead stars into pure energy that illuminates the cosmic night. Chapter 7: The Information Paradox. Stephen Hawking discovered that black holes emit radiation and slowly evaporate. In 1974, Hawking made the startling discovery that black holes aren't completely black. By applying quantum mechanics to the curved spacetime near black holes, he found that they should emit a faint stream of particles and energy. This Hawking radiation is incredibly weak for stellar mass and supermassive black holes, but it suggests that all black holes will eventually evaporate completely, returning their energy to the universe over timescales almost too vast to comprehend. Hawking radiation arises from quantum fluctuations near the event horizon. Quantum mechanics. tells us that empty space is never truly empty but filled with virtual particle pairs that constantly appear and annihilate. Near a black hole's event horizon, one particle from such a pair can fall into the black hole, while the other escapes, becoming real in the process. The escaping particle carries away a tiny amount of energy, while the black hole loses a corresponding amount of mass, according to Einstein's famous equation E equals mc squared. Smaller black holes evaporate faster than larger ones. Paradoxically, the temperature of Hawking radiation is inversely proportional to the black hole's mass. A black hole with the mass of our Sun would have a temperature of only 60 billionths of a degree above absolute zero, making its evaporation time longer than the current age of the universe by many orders of magnitude. But a black hole with the mass of a mountain would be much hotter and would evaporate in fractions of a second in a burst of gamma rays. The information paradox challenges our understanding of quantum mechanics. When matter falls into a black hole, it carries information about its quantum state, the precise arrangement of particles and their properties. If the black hole eventually evaporates completely through Hawking radiation, what happens to this information? Quantum mechanics says information can never be truly destroyed, but general relativity suggests it disappears with the black hole. This paradox has puzzled physicists for decades. Black holes might store information on their surfaces rather than destroying it. One proposed solution to the information paradox is that information falling into a black hole is actually encoded on its two-dimensional surface, the event horizon. This holographic principle suggests that all the information contained in a volume of space can be represented as data stored on the boundary of that space. The black hole's event horizon might act like a cosmic hard drive, storing every bit of information that falls in. The firewall paradox suggests that event horizons might not be smooth. Some physicists have proposed that the event horizon of an evaporating black hole might not be the smooth, empty boundary that general relativity predicts. Instead, it could be a firewall of high-energy particles that would destroy anything trying to cross it. This solution preserves quantum mechanics, but at the cost of one of general relativity's most important predictions about black holes. Hawking's late proposal suggested that event horizons might not exist at all. In his later work, Hawking himself proposed that true event horizons might not exist. Instead, there might be apparent horizons that temporarily trap information and then release it as the black hole evaporates. This would mean that information never truly enters a region from which it cannot escape, resolving the paradox but radically changing our understanding of black holes. The black hole information paradox connects the very small to the very large. This puzzle links quantum mechanics, which governs the smallest particles, to general relativity, which describes the largest structures in the universe. Resolving it may require a theory of quantum gravity that unifies these two fundamental but incompatible descriptions of nature. The paradox shows us that black holes are not just exotic objects in space, but laboratories for testing the deepest laws of physics. Entanglement between particles may play a key role in resolving the paradox. Quantum entanglement, where particles maintain mysterious connections regardless of distance, might provide a solution. Some theories suggest that particles falling into a black hole remain entangled with particles in the Hawking radiation, allowing information to be gradually released as the black hole evaporates. This ER equals EPR conjecture links Einstein-Rosen bridges, wormholes, with Einstein-Podolsky-Rosen entanglement. The paradox has inspired new theories about the nature of spacetime itself. Attempts to resolve the information paradox have led to radical new ideas about reality. Some physicists now suggest that spacetime itself might be an emergent property of quantum entanglement, that the familiar three dimensions of space and one of time might arise from more fundamental quantum information. Black holes, in this view, are not objects in spacetime but rather patterns in the underlying quantum information that creates spacetime. Black hole complementarity suggests that reality depends on your perspective. This principle proposes that the same physical process appears different to different observers. An outside observer sees information spread across the black hole surface and eventually released in Hawking radiation, while someone falling in sees the information pass normally through the event horizon. Both perspectives are correct within their own reference frames, but they describe fundamentally different versions of reality. The paradox may require us to abandon cherished assumptions about nature. Resolving the information paradox might require giving up some of our most basic beliefs about reality. We might need to accept that spacetime is not fundamental, that information can be duplicated, that locality doesn't apply at quantum scales, or that the principles of quantum mechanics need modification. Each potential solution asks us to reconsider what we think we know about the universe. Experimental tests of the information paradox remain far beyond our technology. The Hawking radiation from astrophysical black holes is so weak that it's completely undetectable with current technology. We cannot directly observe black hole evaporation or test whether information is preserved or destroyed. The paradox must be resolved through theoretical insights and consistency with other physical principles rather than direct experimental verification. The search for a resolution continues to drive advances in fundamental physics. The information paradox has motivated the development of new mathematical tools, inspired discoveries about quantum entanglement, and led to fresh insights about the nature of spacetime. Even if we never directly observe Hawking radiation, the theoretical challenge of understanding black holes continues to deepen our knowledge of the universe's most fundamental laws. As you rest in the quiet of night, consider that this ancient puzzle connects the tiniest quantum particles to the largest objects in space. The same quantum mechanics that governs the atoms in your body creates paradoxes when applied to black holes billions of times more massive than the Sun. Somewhere in the darkness of space, black holes are slowly, imperceptibly evaporating, potentially releasing information that fell into them billions of years ago. Whether that information survives or is destroyed forever remains one of the deepest mysteries in physics, a cosmic riddle written in the language of quantum mechanics and gravity, waiting patiently for human insight to decode its meaning. Chapter 8: Ripples in Spacetime. Gravitational waves are ripples in the fabric of spacetime itself. Einstein's theory of general relativity predicts that accelerating masses should create waves in spacetime, much like a stone thrown into a pond creates ripples on the water's surface. These gravitational waves travel at the speed of light, carrying energy and information about the cosmic events that created them. Unlike electromagnetic waves, which can be absorbed or scattered, gravitational waves pass through matter almost completely unimpeded, reaching us directly from the most violent events in the universe. Binary black holes spiral together while emitting gravitational waves. When two black holes orbit each other, they gradually lose energy by radiating gravitational waves. This energy loss causes their orbits to decay, bringing them closer together over millions or billions of years. As they approach each other, they orbit faster and faster, emitting stronger gravitational waves in a process that accelerates until the final, catastrophic merger. The entire process follows precise mathematical predictions from Einstein's equations. The final merger of two black holes releases enormous amounts of energy. In the last fraction of a second before two black holes merge, they can orbit each other hundreds of times per second. The collision itself releases more energy in gravitational waves than all the stars in the observable universe emit in light. This energy comes from the conversion of the black hole's orbital motion into ripples in spacetime, demonstrating mass-energy equivalence on the most dramatic possible scale. LIGO detected the first gravitational waves in 2015. The Laser Interferometer Gravitational Wave Observatory made history by detecting gravitational waves from a binary black hole merger 1.3 billion light-years away. The waves caused the LIGO detectors to change length by less than 1/10, 0.000 to the width of a proton, yet this incredibly tiny distortion was precisely what Einstein's theory predicted. The detection opened an entirely new window on the universe, allowing us to observe cosmic events that produce no light. Gravitational waves carry information that light cannot provide. Unlike electromagnetic radiation, gravitational waves are not absorbed or scattered by matter. They reach us directly from the hearts of merging black holes, neutron star collisions, and other extreme events. This allows us to observe regions of the universe that are completely opaque to light and to study physics in conditions far more extreme than anything we can create on Earth. The chirp of a gravitational wave reveals the masses of merging objects. As two black holes spiral together, the frequency of their gravitational waves increases in a characteristic pattern called a chirp. By analyzing this chirp, scientists can determine the masses of the merging objects, their spins, and their distance from Earth. Each gravitational wave detection is like a cosmic fingerprint, revealing the detailed properties of objects billions of light-years away. Merging black holes create new black holes with specific properties. When two black holes merge, they form a single larger black hole. The mass of the final black hole is less than the sum of the original masses because some mass is converted into gravitational wave energy. The spin and other properties of the final black hole depend on the masses, spins, and orbital characteristics of the original pair, following precise mathematical relationships that test our understanding of general relativity. Gravitational waves from neutron star mergers were first detected in 2017. The collision of two neutron stars creates gravitational waves with different characteristics from black hole mergers. Unlike black hole mergers, which produce only gravitational waves, neutron star mergers also create electromagnetic radiation, gamma-ray bursts, and heavy elements like gold and platinum. This multi-messenger observation allowed astronomers to study the same event with both gravitational wave detectors and traditional telescopes. The ring-down phase reveals the properties of the final black hole. After two black holes merge, the newly formed black hole undergoes a brief period of vibration called the ring-down phase. During this time, the distorted black hole emits gravitational waves as it settles into its final, stable state. The frequency and decay rate of these waves are determined entirely by the mass and spin of the final black hole, providing a direct test of Einstein's theory in the strong field regime. Gravitational wave astronomy has revealed unexpected populations of black holes. Before gravitational wave detections began, astronomers knew of only a few dozen stellar-mass black holes in our galaxy. Gravitational wave observatories have now detected dozens of black hole mergers, revealing that black holes are more common and more massive than previously thought. Some of the detected black holes have masses that were difficult to explain with existing theories of stellar evolution. Future gravitational wave detectors will observe cosmic history. Next generation gravitational wave Observatories will be sensitive enough to detect black hole and neutron star mergers throughout most of the observable universe. This will allow us to trace the formation and evolution of compact objects across cosmic history, from the first stars to the present day. We'll be able to observe the universe when it was only a few 100 million years old, long before the first light-emitting galaxies formed. Space-based gravitational wave detectors will access new frequency ranges. Ground-based detectors like LIGO are sensitive to high-frequency gravitational waves from stellar mass objects. Space-based detectors like the proposed LISA mission will detect low-frequency waves from supermassive black hole mergers, extreme mass ratio and spirals, and possibly even from the early universe itself. These observations will probe entirely different physical processes and cosmic epochs. Gravitational waves might carry signatures from the early universe. The cosmic microwave background radiation shows us the universe as it was about 380,000 years after the Big Bang, when it first became transparent to light. But gravitational waves can travel freely through the universe from much earlier times, potentially carrying information about cosmic inflation, phase transitions, or other exotic processes in the first moments after the Big Bang. The detection of gravitational waves confirms Einstein's century-old prediction. Einstein himself doubted whether gravitational waves would ever be detectable, calling them so weak that they would never be observed. The successful detection of these ripples in spacetime represents one of the greatest triumphs of theoretical physics, confirming a prediction made a century ago using nothing but mathematics and insight into the nature of space and time. Even now, as you rest peacefully, gravitational waves from distant cosmic collisions are passing through your body, through the Earth, through the entire solar system. These ripples in spacetime carry stories of black holes that merged billions of years ago, their final dance encoded in the gentle stretching and compression of space itself. The waves are so subtle that they barely disturb even our most sensitive instruments, yet they connect us directly to the most energetic events in the universe. In the silence of night, spacetime itself whispers tales of cosmic violence and beauty, of matter and energy transformed into pure geometry, of Einstein's equations made manifest in the fundamental structure of reality. Chapter 9. The First Image. The Event Horizon Telescope captured the first image of a black hole shadow in 2019. After decades of theoretical predictions and indirect observations, humanity finally saw direct visual evidence of a black hole. The image showed the supermassive black hole at the center of the galaxy M87, located 55 million light-years from Earth. What we saw was not the black hole itself, but its shadow silhouetted against the bright glow of superheated matter in its accretion disk, exactly as Einstein's equations had predicted. The M87 black hole appears as a bright ring with a dark center. The iconic image shows a glowing ring of orange and yellow light surrounding a dark circular region about 2.5 times larger than the event horizon itself. This dark region is the black hole's shadow, created because light from behind the black hole is bent around it, while light from the bright accretion disk creates the luminous ring. The asymmetry in the ring's brightness reveals that the disk is rotating, with one side moving toward us and the other away. Creating the image required a planet-sized telescope. No single telescope could resolve details as small as a black hole's event horizon from such a vast distance. The Event Horizon Telescope is actually a network of radio observatories around the world, from Hawaii to Chile to Antarctica, all observing simultaneously. Using a technique called very long baseline interferometry, these telescopes work together as if they were a single instrument the size of Earth. The black hole's shadow is larger than our entire solar system. The M87 black hole has a mass of about 6.5 billion suns and an event horizon roughly 120 billion kilometers across. Its shadow, which appears about 2.5 times larger due to gravitational lensing effects, could easily contain our solar system, with room to spare. Despite this enormous size, the black hole appears smaller than a donut on the Moon when viewed from Earth, requiring extraordinary precision to image. The image confirms predictions made decades before it was possible to test them. The appearance of the M87 black hole matches computer simulations based on Einstein's general relativity with remarkable accuracy. The size, shape, and brightness distribution of the shadow all agree with theoretical predictions, providing one of the strongest tests of general relativity in the extreme gravitational environment near a black hole. It's a triumph of theoretical physics confirmed by observation. 8 observatories on 4 continents participated in the historic observation. The Event Horizon Telescope network included the Atacama Large Millimeter Array in Chile, the James Clerk Maxwell Telescope in Hawaii, the Large Millimeter Telescope in Mexico, and 5 other facilities. For several days in April 2017, these telescopes observed M87 simultaneously, recording petabytes of data that would later be processed to create the historic image. The data processing required years of careful work. Creating an image from the raw observational data was like assembling a jigsaw puzzle with most of the pieces missing. Multiple teams of scientists worked independently to process the data, using different algorithms and techniques to ensure the results were reliable. The computational challenges were immense, requiring specialized software and months of processing time on powerful computer clusters. The black hole's magnetic field creates the bright jets extending thousands of light years. The M87 black hole is famous for its spectacular jet, a stream of high-energy particles extending over 5,000 light years from the galaxy's center. The Event Horizon Telescope observations revealed how magnetic fields near the event horizon help launch and collimate this jet, solving a long-standing mystery about how black holes can influence regions much larger than themselves. Polarized light observations revealed the magnetic field structure. Follow-up observations with the Event Horizon Telescope measured the polarization of light from the M87 black hole's accretion disk. This polarization acts like a fingerprint of magnetic fields, revealing their strength and direction near the event horizon. The observations showed highly organized magnetic field lines that help explain how the black hole can launch such powerful jets. The technique opened a new era of black hole imaging. The success with M87 proved that direct imaging of black holes is possible with current technology. The Event Horizon Telescope has since imaged other black holes and will continue to provide unprecedented views of these exotic objects. Future improvements to the network will allow for even more detailed images and the ability to make movies, showing how black hole accretion disks change over time. Sagittarius A, our galaxy's central black hole, was imaged in 2022. 3 years after the M87 image, the Event Horizon Telescope released the first image of the supermassive black hole at the center of our own Milky Way galaxy. Sagittarius A* is much smaller and more variable than M87's black hole, making it technically more challenging to image. The resulting picture showed a similar glowing ring structure, confirming that black holes at different scales share common characteristics. The images provide a new laboratory for testing physics. Black hole images allow scientists to test general relativity in conditions impossible to recreate on Earth. The extreme gravity near event horizons provides a natural laboratory for studying how spacetime behaves under the most extreme conditions in The universe. Future observations will continue to probe whether Einstein's theory holds up in these exotic environments. Citizen scientists and students contributed to the historic achievement. The Event Horizon Telescope project involved not just professional astronomers but also students, postdocs, and volunteers from around the world. The international collaboration demonstrated how modern astronomy brings together people from different countries, cultures, and career stages to tackle some of the universe's biggest mysteries. The images represent humanity's first direct look at the point of no return. For the first time in human history, we can see the boundary between the known universe and regions from which no information can ever return. The event horizon remains invisible, hidden behind its shadow, but we can see exactly where spacetime becomes so curved that even light cannot escape. It's a view of one of nature's most fundamental boundaries, the edge of the knowable universe made visible at last. As you drift toward sleep tonight, picture that glowing ring of light surrounding perfect darkness, an image that represents one of humanity's greatest scientific achievements. Somewhere in the constellation Virgo, that supermassive black hole continues its ancient dance, bending light and time around its invisible event horizon. The photons that created that historic image traveled for 55 million years to reach our telescopes, carrying with them direct evidence of Einstein's most profound insights about the nature of space and time. In observatories around the world, scientists continue to peer into the cosmic dark, using the entire Earth as a telescope to reveal the hidden architecture of the universe, one pixel of shadow and light at a time. Chapter 10. Stellar Mass Wanderers. Stellar mass black holes are scattered throughout our galaxy like invisible islands. Most black holes in the Milky Way are the remnants of massive stars that ended their lives in supernova explosions millions or billions of years ago. These stellar wanderers, typically containing between 3 and 20 times the mass of our Sun, drift silently through space on orbits inherited from their progenitor stars. Astronomers estimate that our galaxy may contain as many as 100 million of these dark objects, most of them completely isolated and detectable only through their gravitational effects. The closest known black hole to Earth lies about 1,000 light-years away. This nearby black hole, designated Gaia BH1, was discovered through its gravitational influence on a companion star. At 10 times the mass of our Sun, it orbits with its stellar companion every 185 days. Despite being relatively close on cosmic scales, this black hole poses no threat to Earth. Even if it was somehow transported to our solar system, its gravity would only affect objects that came very close to it. Most stellar mass black holes are detected through X-ray emissions from companion stars. When a black hole exists in a binary system with a normal star, it can gravitationally strip material from its companion. This stolen matter forms an accretion disk that heats up to millions of degrees, emitting bright X-rays that we can detect from thousands of light-years away. These X-ray binaries flicker and vary in brightness as the accretion rate changes, creating distinctive signatures that reveal the presence of the invisible black hole. Some black holes wander alone through interstellar space. Not all black holes exist in binary systems. Many are solitary objects that received kicks from their supernova births or were ejected from binary systems through gravitational interactions. These isolated black holes are much harder to detect because they produce no light of their own and have no companion stars to steal material from. They reveal themselves only occasionally through gravitational microlensing when they pass between Earth and a more distant star. Microlensing events can reveal invisible black holes. When a black hole passes nearly in front of a background star as seen from Earth, Its gravity acts like a lens, temporarily magnifying and distorting the star's light. These microlensing events typically last for weeks or months and can reveal not only the presence of the lensing object but also its mass. Several candidate black holes have been discovered this way, though confirming their nature often requires years of careful observation. Rogue black holes may have been ejected from their birthplaces. Asymmetric supernova explosions can give newly formed black holes a kick velocity of hundreds of kilometers per second, enough to eject them from their birth clusters or even from the galactic disk entirely. These rogue black holes wander through the galaxy on highly elliptical orbits, occasionally passing through the disk plane before returning to the sparse halo regions. They represent the nomads of the black hole population. Binary black hole systems can merge after billions of years of orbital decay. When two massive stars in a binary system both become black holes, they form a binary black hole system that gradually loses energy through gravitational wave emission. Over time scales of millions to billions of years, their orbits shrink until they finally merge in the catastrophic collisions detected by LIGO and other gravitational wave observatories. Before LIGO, we had no direct evidence that such systems existed in large numbers. Some stellar mass black holes may have unusual formation histories. Not all stellar mass black holes form from the direct collapse of single massive stars. Some may result from the merger of two smaller, compact objects, such as neutron stars or smaller black holes. Others might form through more exotic processes, such as the collapse of very massive stars that never underwent nuclear burning. These alternative formation channels could produce black holes with masses and properties different from those predicted by standard stellar evolution. Intermediate mass black holes bridge the gap between stellar and supermassive scales. Astronomers have found evidence for black holes containing hundreds to thousands of solar masses. More massive than typical stellar mass black holes, but much less massive than the supermassive giants in galaxy centers. These intermediate mass black holes might form through the merger of multiple stellar mass black holes in dense star clusters, or they might be the seeds from which supermassive black holes grow. Black holes can be ejected from globular clusters through gravitational interactions. Dense star clusters containing thousands of stars can harbor multiple stellar mass black holes formed from the cluster's most massive members. Gravitational interactions between these black holes can result in some being ejected from the cluster at high speeds. These ejected black holes become wanderers in the galactic halo, carrying with them information about the dynamics of their birth environments. Future surveys will discover many more stellar mass black holes. The Gaia Space Telescope and other astronomical surveys are revolutionizing our ability to find black holes through their gravitational effects on nearby stars. By precisely measuring stellar positions and motions, these surveys can identify stars that appear to be orbiting invisible companions. In the coming decades, we expect to discover thousands of new stellar mass black holes, greatly expanding our census of these elusive objects and helping us understand their distribution throughout the galaxy. Some black holes may have formed from the very first stars in the universe. Population 3 stars, the first generation of stars that formed when the universe contained only hydrogen and helium, could have been much more massive than any stars we see today. When these primordial giants died, they may have formed black holes that still exist in our galaxy today. These ancient black holes would carry within them information about the early universe, making them cosmic time capsules from an era when the cosmos was very different from today. Black hole neutron star binaries create unique gravitational wave signatures. When a stellar mass black hole orbits with a neutron star, their eventual merger produces gravitational waves with characteristics distinct from both black hole and neutron star mergers. These systems are rarer than pure black hole binaries, but they offer unique opportunities to study the physics of dense matter and the formation of heavy elements in the universe. Stellar mass black holes can have complex spin orientations. Unlike supermassive black holes, which typically align their spins with their host galaxy's rotation, stellar mass black holes can have spins pointing in any direction. This reflects their formation through supernova explosions and their subsequent evolution through binary interactions. Measuring these spin orientations provides clues about the violent processes that created these objects and shaped their subsequent evolution. Some black holes may exist in hierarchical triple or multiple systems, while most known black holes exist in simple binary systems. Some may be part of more complex configurations with multiple companions. These systems can undergo intricate gravitational dances that sometimes result in the ejection of one component or dramatic changes in orbital properties. Such systems provide natural laboratories for studying the complex dynamics of strong gravitational fields. Black holes preserve the chemical signatures of their progenitor stars. Although we cannot directly observe the material inside a black hole, the properties of the accretion disk and jets can reveal information about the composition of infalling material. This allows astronomers to infer something about the chemical makeup of the original star that collapsed to form the black hole, connecting these exotic objects to the stellar evolution processes that created them. The search for primordial black holes continues throughout our galaxy. These hypothetical objects, formed in the early universe rather than from stellar collapse, could exist with a wide range of masses. If they exist, primordial black holes might make up part of the mysterious dark matter that dominates our galaxy's mass. Detecting even one confirmed primordial black hole would revolutionize our understanding of both black hole formation and the early universe. Even now, as you rest in the quiet darkness, stellar mass black holes drift silently through the space between stars, following orbits that may not bring them near another object for millions of years. Some travel alone, invisible sentinels carrying within their event horizons the compressed remnants of ancient suns. Others dance in cosmic partnerships, slowly spiraling toward eventual merger in events so energetic they shake the very fabric of spacetime. These wandering dark objects represent the final chapter in the lives of the galaxy's most massive stars, scattered like seeds throughout the Milky Way, each one a testament to the awesome power of gravity and the exotic physics that governs the universe's most extreme environments. And now, as we near the end of our gentle journey through the realm of black holes, the cosmic mysteries begin to fade like distant stars behind gathering clouds. We've wandered together through the violent births of these dark objects, witnessed the elegant mathematics that describes their event horizons, and contemplated the profound puzzles they present to human understanding. You've drifted past stellar mass wanderers scattered throughout our galaxy, each one the compressed heart of a star that once blazed with nuclear fire. You've visited the supermassive giants that slumber in the centers of galaxies, anchoring vast stellar systems in their gravitational embrace. You've seen how these objects bend space and time around them like cosmic sculptors, creating ripples in the fabric of reality itself that we can now detect from billions of light years away. Tonight, you've witnessed how black holes feed on the universe around them, transforming matter into pure energy through processes more efficient than any earthly technology. You've encountered the information paradox that challenges our deepest understanding of quantum mechanics and reality itself. You've observed the first photographs ever taken of a black hole's shadow, images that represent humanity's first direct glimpse of these cosmic boundaries between the known and unknowable. Through it all, you've seen how black holes are not the destroyers of science fiction, but rather nature's most elegant expressions of gravity's power. They are cosmic laboratories where the familiar laws of physics are stretched to their limits, revealing new aspects of reality that we are only beginning to understand. They connect the quantum world of the very small to the cosmic realm of the very large, bridging scales of existence in ways that continue to surprise and humble us. You are connected to these distant objects in ways both poetic and profound. The iron in your blood was forged in the nuclear furnaces of massive stars, some of which may have ended their lives as the very black holes we've explored tonight. The calcium in your bones, the oxygen you breathe, even the carbon that forms the backbone of your DNA, all were created in stellar cores and distributed by supernova explosions that may have left behind these dark remnants. As you rest now, somewhere in our galaxy, matter is falling past an event horizon, crossing the ultimate boundary from which no information can ever return to our universe. Gravitational waves from ancient black hole mergers are passing through your body right now, carrying stories of cosmic collisions that happened before the Earth was born. In the center of our own Milky Way, Sagittarius A** sits patiently, a 4 million solar mass giant that has watched over the birth and death of countless generations of stars. The universe continues its ancient dance, with black holes serving as both destroyers and creators. Endings and beginnings, darkness that illuminates the deepest truths about space, time, matter, and energy. They remind us that the cosmos is far stranger and more wonderful than our everyday experience. Suggests, filled with objects and phenomena that challenge our imagination and expand our understanding of what is possible. Tonight, as you drift into peaceful sleep, you carry with you glimpses of these cosmic mysteries. In your dreams, perhaps you'll wander among the event horizons we've explored, drift through accretion disks, glowing with the light of doomed matter, or float in the gentle darkness between stars where solitary black holes trace their silent paths through space and time. The black holes will continue their patient existence long after you wake, long after human civilization has passed into cosmic history. They are among the most permanent objects in the universe, slowly evaporating through Hawking radiation over timescales that make the current age of the cosmos seem like a brief moment. In their dark depths, they preserve the ultimate secrets of matter, energy, space, and time, waiting perhaps forever for minds capable of unlocking their mysteries. Sleep well, cosmic wanderer. Dream of event horizons and gravitational waves, of singularities and information paradoxes, of the beautiful darkness that teaches us so much about the light. Tomorrow the universe will still be full of mysteries, still be calling to the curious, still be revealing its secrets to those patient enough to listen to the whispers of spacetime itself. Good night, and may your dreams be filled with wonder.